Welcome to this lesson of a linear algebra class. And yeah, so this the first previous videos I've been doing, and everything was supposed to prepare you for this actual session, right? So this is basis, and it comes with a lot of definitions. So I've gone through all those definitions, what it means to be linearly dependent and the rest, and linearly independent, right? So a basis for a vector space V, so assuming I have a vector space maybe R2, is a subset B, beta, or maybe B, you can call it beta or something, which belong to the same vector space, such that one, the set you're talking about, or what set you call basis, is actually linearly independent, and two, beta spans V. I've mentioned this in one of our previous videos that when we say something spans a vector space, it means every element you have here in V can be written as a linear combination of vectors in beta. All right, that's what I mean. Or each vector, so I have it here, or each vector in V is a linear combination of vectors in beta, right? So maybe an example is, the basic idea is R2 has a basis as 1 0. This is very straightforward. I mean, most books will state this. Why? Because if you look at this, we've done this in our previous videos, this is linearly independent, this set. And again, every element you have in R2 is written by, so every V that belongs to R2 can be written up by V is equal to maybe AB or maybe A1, B1. I mean, in a two-dimensional, like, so A can be any number. So I've written a general form. You can write it as maybe 2, 3, 4. So in case where A is equal to 3 and B is maybe equal to -1, you have the vector to be equal to 3, -1, right? So I mean, in all cases, you have some number here, some number here, right? And what this means is that realize that AB can be split into A into 1 here, then I bring 0, plus B into 0, 1. And if you look at this, this is a linear combination of elements you have in beta, right? So every element you have, or every vector you have in R2 is is a linear combination of vectors 1 0 and 0 1. So it means that the span of beta actually give R2, and then we talked about the span. The span is what we mean by all the set of linear combinations you can get for these vectors you have here. And all the set of linear combinations you can get for this set will produce all vectors in R2. I don't know if this makes sense. So it means that the basis for R2 in this particular example is actually this set, right? Now let's look at more intuitive ideas here. Now, assuming I have some vector S, I mean some set S with some vectors, and I want to find a basis for the span of S. What I want to do is make sure that I get some set of vectors such that their linear combination will give me 0 only when the scalars are zeros, right? So when you have some set of vectors like this, and these are just different random vectors, what you can do, one, if you reason, maybe you can run this in MATLAB or maybe any other programming language to use a row reduce echelon form function, and then it will just reduce it and tell you what, or maybe it will show you what to choose as your basis. Now, a very little trick you can use is to form a matrix, and I said this in our previous videos that a matrix should contain all the columns should contain all these vectors. So the first column should contain this first vector, the second column should contain that, and the third column should contain that one. And I have 1 2 1 -1 1 -2. Then what you're going to do with this case is that since you have this, and you're going to have maybe some values, scalars, maybe a1, a2, a3, a4, a5, so a1, a2, a3, a4, a5 should give you the 0 vector, right? And since the part you have here, I mean the elements you have here is just 0 0, you can choose not to bring all these and then try to row reduce what you have in here. And like I said, the way you do the row reduction is that you try to change or make sure that all the elements under the first leading value everything under it beneath it is 0. So if you look at the first value, the second row has a 0 under it, so we won't touch the second row. Now the next thing to do is to work on this guy. You're going to make sure that this value is actually 0 under that. And in that case, what you're going to do is, first I said stand on the first row, the row you don't want to touch. So row 1, then minus row 3. And if you do that, these two will subtract and then you get 0 there, right? So this will give you a different matrix, and that's going to be row 1. You just write row 1. So I mean, let me just write something here for you too. So what is going to happen is that you have your row 3 should be equal to this, and this is going to generate a new matrix that's going to be 1 0 1 1 negative 1, and then you won't touch the row 2 because already beneath that you have a 0. And so I'm going to have 0 here because when these two subtract, I'm going to get 0. When these two subtract, I'm going to get negative 1, right? So I'm going to have 0 minus 1, that's going to give you negative 1. And then when these two also subtract, I'm going to get another negative 1. And then when these two subtract, so I'm just performing row 1 minus row 3. I'm going to have 0. And then when these two subtract, I'm going to have 1. I believe, yeah. Then I'm done with the first row. Now I'll go to the next row, the next leading value in the next row. And the next leading value here is 1. So if here was 0, then we'll have to interchange these two because this has a value, right? But you know, those are some of the tricks you can think of. So here has a value 1. I have to make sure that beneath that 1, everything else is 0. And here we have negative 1 here. So what can I do between these two numbers such that I will get this guy? I mean, everything I'm doing is between these two numbers. So either I add them or maybe I do something else. So I'm going to add these two numbers. So I'm going to have row 3. Now the same thing, we are working on that row 3 should transform to row 2 plus row 3. So what this means is that our new row 3 that we need should be the original row 2 plus the original row 3, and that should give you row 1. So you write it back, and I'm going to have negative 0 1 1 2 1, and then this should give me 0. And when I add these two, I should get 0. When I add these two, I should get 0 again. When I add these two, I should get what? 2. And when I add these two, I'm supposed to get 2. So now the next row I look at is the last row, and the leading value is 2, but there's no other values beneath that. So we are done, right? So now this method is very tricky. So how are you going to choose your how do I call it, your basis here is that you're going to choose some particular columns, and that columns will correspond to the vectors you place in those columns, right? Now this column, we place the vector 1, this 1 in that, and then we place vector 2 in column 2. So that's what we did, right? So you look at all rows and search the leading values, right? So if I come to row 1, I have a leading value 1, and it's in column 1. So what I'm going to do is the basis is going to contain the first vector I chose to put in the first column. So in column 1 or maybe row 1, I have a leading value 1 there. So I'm going to pick, okay, that column. I mean, this is a trick we use, okay? So just follow that. This first column, and when I pick that, I'm going to pick the vector that I placed in that first column. And that original vector is coming from here, right? So I'm going to put 1 0 1 here. This whole thing is coming from matrix algebra, and I really don't want to go much do or maybe say much about that. I go to the next row. I have the leading value to be this 1, and that leading value is on column 2, right? So I go and pick the vector that I place in column 2, and that is 0 1 1. Then I go again and look for the next. This tends to be the last row. And in the last row, the leading value is 2 or maybe you can divide this whole thing by 2 and you have 1 there. It happens sometime, but my main focus is to just look for the leading values. It's 2, and this is happening on which column? You have 1, 2, 3, 4, column 4. So I'm going to pick the vector that I place in column 4, and that is this vector, because when I count I have 1, 2, 3, 4. This is what I picked. 2, 1. And I asked myself if there is any other row, so I just went through the row 1, row 2, and row 3, and that's all that it takes, right? So the set of these vectors that I've been able to pick from the leading values are what we call that will constitute the basis for this particular set. All right, so it means all elements that will belong to the span of this S. What it means is all vectors that you can write as a linear combination of these things also will belong to the span of this basis. If you remember, we said that the basis actually spans a vector space, right? So if this is the basis for this set S, then it means that all the elements in this span, or elements that you can write as a linear combination of elements, or maybe vectors that you can write as a linear combination of these kind of vectors, those vectors can be written as a linear combination of this same set of vectors. It works. I don't really want to bring out an example, but that really works. Okay. Now I have another set of vectors here that I want to work with. So find a basis for this, the span of S. Now to work with this, I'm going to really go fast. I said first form a matrix with these columns, right? And I'm going to have 2, 5, 8, 3, 6, 9. And it turns out to be the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Now what I'm going to tell you to do is make sure that you understand these processes, because this is the same process you're going to use to find the rank of a matrix and the dimension of the rank of a matrix and those things, right? Now this first, I'm going to transform it to what? I'm going to make sure that all the elements or all the numbers below 1 are 0. So you stand on this one, make sure that every number that is below that is 0. So between 1 and then row 2, what's going to happen is I'm going to do 4 times row 1 minus row 2, and that should give me my new row 2. And between this and that 2, I'm going to have 7 times row 1 minus row 3, and that's going to give me my new row 3. So in all, I'm going to have a new matrix that will be like this. I have 1, 2, 3. I don't touch it, and I know 4 times row 1, so I'm going to have 4 here minus 4. That's going to give me 0. 4 times 2, that is 8 minus 5, that's going to give me 3. 4 times 3, that is 12 minus 6, that's going to give me 6. Then I come to row 1 and then row 3. 7 times row 1 is 7 minus 7 is 0. And then 7 times 2 is 14 minus 8 is 6, right? 14 minus 6 should be 8. 14 minus 8 should be 6, sorry. And then 7 times 3 is 21 minus 9 is supposed to be 12, right? And that is for the first row. Now I'm going to reduce this again to something else. Now I'm going to make sure that if you come to the first one, everything beneath it is 0. So I have to come to the next leading value, that is 3, and beneath that I have 6. So what I'm supposed to make sure is to make sure that beneath 3 we have 0, right? And what you can do to that is to transform this with this equation that 2 times row 2 minus row 3 should give me my new row 3. And so I'm going to have, let me write 1, 2, 3, 0, 3, 6, 0. And then this is, if you can do this. 2 times 0 minus 0 is still 0. So that's why I just have it here. Now I'm going to have 2 times 3, which is 6, minus this 6, which is 0. And 2 times 12 is 12. 2 times 6 is 12. Minus 12 is actually 0. So, So here, what we're going to do is we're going to locate the leading values in each row. So I come to row 1. Leading value is 1. So I go to the first the vector that I place in column 1, and that is this vector. So the basis here is actually supposed to be so I'll put the first vector there, 1 4 7, and I go to row 2. Which one is the leading value? That is 3. And which one did I place in that row, that column? And that is this vector, 2 5 8. And you come to row 3, there's no leading value, you don't have a big value, so everything here is 0. So what you're going to do is you close it, and this becomes the basis for this set S, right? So yeah, that is the way you find basis for a particular set. Like I said, you're going to apply this same knowledge on finding the basis for the range of a matrix, or maybe finding the rank of a matrix. Stay tuned, and don't forget to subscribe to my channel if you have not subscribed. See you in our next video.